In this lesson, we're going to talk again about how the derivative affects the shape of a graph, but more specifically, we're going to focus on the second derivative. So the second derivative is really going to tell us about the concavity of the original graph. So when we're dealing with concavity, there are two different types of concavity. There's concave up and there's concave down. So on the left, we have graph f, and that is showing us a concave up function. Concave up is going to look like a cup. So I will write cup just so you remember that. So concave up looks like a cup. And basically, if I were to draw tangent lines to this curve, all of my tangent lines would be drawn below the curve. So if the tangent lines are drawn below the curve, it is concave up. I have a concave down function with function g over here, and that is going to look like a frown. So concave down looks like a frown. If I'm drawing my tangent lines and my tangent lines are above the curve. Okay, so when I have tangent lines below the curve, I have concave up. When I have tangent lines above the curve, I have concave down. So let's look a little bit more specifically at these. So here are the same exact graphs. We have f and we have g. So if I'm looking at the slope of the tangent lines, so as I make tangent lines from left to right, the slope of these tangent lines is increasing. So since the slope of these tangent lines is increasing, that means that the derivative of f, which is f prime, is an increasing function, and therefore the second derivative is going to be positive. So anytime we have an increasing function, the derivative that corresponds with that directly is going to be positive. Okay, so on g down here, as I go from left to right and I draw the tangent lines, the slope of these tangent lines are decreasing. So that means that the derivative of g, which is g prime, is a decreasing function, and therefore the derivative of that, which is g double prime, is going to be negative. Okay, this will make a lot more sense once we actually do examples. Okay, so just here's a function here, and we can see the different intervals of concavity. So from A to B, we have concave down, right? Looks like a frown. If I draw tangent lines, they're all going to be drawn above the curve. From B to C, I have concave up, looks like a cup. C to D, concave down. D to E, concave up. E to P, concave up. P to Q, concave down. Okay, so the concavity test is basically telling us how we figure out if it's concave up or down by taking the second derivative. So when I take the second derivative, if the second derivative is positive, if it's greater than 0, then the original graph is concave up on that interval. When I take the second derivative, if it's negative, then my original graph would be concave down on that interval. So this is very similar to when we did the first derivative and we were finding the intervals of increasing and decreasing, but now we're finding the intervals of concave up and concave down. So here's an example. Determine the intervals on which the function y equals 10x cubed minus x to the fifth is concave up or concave down. So again, we're going to kind of use the same method that we used when we did the intervals of increasing and decreasing with the first derivative. So we just need to make sure that we remember that increasing and decreasing goes with the first derivative, concavity goes with the second derivative. So since I'm dealing with concavity here, I have to find the second derivative. So first thing I'll do is find the first derivative. So y prime is going to be 30x squared minus 5x to the fourth. Okay, I'm now going to take the second derivative. So y double prime is going to be 60x minus 20x to the third. So I'm just going to box this because this is the one that we care about. Okay, so we had to find both because we had to get the first derivative to get to the second. So similar to what we did with the first derivative with our increasing, decreasing, we have to find our second derivative critical points. Okay, so when we found the critical points in the lesson before, we took the derivative and we set it to 0 and wanted to see where it equaled 0 or didn't exist. We're going to do the same thing, but with the second derivative. So here, the second derivative, it is a polynomial. There's going to be nowhere where it doesn't exist. So I'm going to set this equal to 0. So I'm going to factor out a 20x. So now I'm left with 3 minus x squared, set it equal to 0. So I get x is equal to 0 from this 20x. And then if I solve 3 minus x squared equals 0, I'm going to get that x is equal to plus or minus the square root of 3. Okay, so I have 3 critical points here. I have 0, square root of 3, and negative square root of 3. So similar to how I wrote a chart for the increasing decreasing with like f and f prime, I'm going to write a similar chart. So here's f and here's f double prime. So what I'm going to do here is put my critical points along the bottom. So since there's no closed interval, I'm going to keep this one as like negative infinity. So my smallest number is negative root 3. So that's going to go first. Then I have 0. Then I have root 3. Okay, so I want to keep space on each side. So what I'm doing here is I'm picking a number that is going to be less than the square root of 3, and I'm going to plug that into the second derivative. So I can plug it into here, or I can plug it into the simplified, okay, which is where I usually like to plug it in. I don't care about the number, I care about the sign. So if it's positive, I'll put a plus. If it's negative, I'll put a minus. The original function, if it's plus for the second derivative, the original function will be concave up, and if it's negative, it'll be concave down. So I'm going to take a number that's less than negative root 3, so let's say negative 2, and I'm going to plug it into here. So again, I only care about the sign, I don't care about the actual value. So 20 times negative 2 is going to be a negative number. 3 minus a negative 2 squared is going to be another negative number. So I'm going to multiply a negative and a negative, which is going to give me a positive. So since the second derivative is positive, that means that the original function here is going to be concave up. I'm going to pick a number between negative root 3 and 0. So let's say negative 1. I'm going to plug that in. I'm going to do 20 times negative 1. So negative 3 minus negative 1 squared is a positive. So a negative times a positive is a negative. This is going to be concave down. A number between 0 and root 3. So I'll pick 1. I'll plug it in here. This will give me a positive number and a positive number. So I have positive, concave up. And then pick a number greater than root 3. So let's say 2. I get a positive number here. I get a negative number here. So negative, and this is concave down. So we would say that the intervals, it would be concave up from negative infinity to negative root 3. And then it's also concave up from 0 to root 3. And then it's concave down from negative root 3 to 0. And then it's concave down again from root 3 to infinity. Okay, so you can see that this is very similar to our increasing and decreasing intervals. Okay, so when you have concavity, you have points of inflection. Points of inflection are where the concavity changes. So we can see on this graph here, we have a concave down function. And then when we get to this red dot, it kind of switches and it becomes concave up. And then at this red dot, it switches and is concave down, and then it switches and becomes concave up. So those dots where it's switching are called inflection points. And that is where the concavity changes. So let's look at this example. So find the points of inflection for the function y equals cosine x in the interval from 0 to 2 pi. Okay, so in order to find inflection points, we have to first find the second derivative, and we have to see where the concavity is changing, if it changes at all. So first thing we'll do is take the derivative. So my first derivative of cosine x is going to be negative sine x, but I have to find the second derivative. So that's going to be negative cosine x. So I'm just going to box that since we're using that one. Okay, now we have to find our second derivative critical points. So we're going to take negative cosine x, set it equal to 0. So we're trying to figure out where is the cosine equal to 0, and within this interval from 0 to 2 pi. So that's going to be at pi over 2 and 3 pi over 2. So those are my critical points. So now I'm going to make a f and f double prime little chart here. Since I have a closed interval, I'm going to have 0 as my starting point. I have pi over 2. Then I have 3 pi over 2. And then I have 2 pi. So just like before, what we're going to do is just pick values that are within these intervals and plug them into the second derivative and check for the sign. So if I pick a number between 0 and pi over 2 and I plug it into the second derivative, that is going to give me a negative, which means that it's concave down. A number between pi over 2 and 3 pi over 2, if I plug that in, so whatever, like pi, negative cosine of pi, that's going to be positive, and that's going to be concave up. And then a number between 3 pi over 2 and 2 pi, plug it in, we get negative, so that's going to be concave down. Okay, so points of inflection happen where it changes from concave up to concave down, or vice versa, concave down to concave up. So I can see that it goes from concave down to concave up at pi over 2. So I have I call them POI, so point of inflection at x equals pi over 2. And I have another point of inflection, because it goes from concave up to concave down, at 3 pi over 2. So usually, because it's called a point of inflection, we will write them as points. So that's pi over 2. And if I plug pi over 2 into my original function, right, cosine of pi over 2 is going to give me 0. And the cosine of 3 pi over 2 is going to give me 0. Okay, so my points of inflection are here. All right, let's look at, okay, this is the graph of what we just figured out. And we can see here, this is my original graph, and I can see that here it's concave down, and then at pi over 2, it flips to concave up, and then at 3 pi over 2, it flips back to concave down. All right, let's look at this other example here. So find the points of inflection. So again, start off by taking the first derivative. So this is going to give us 15x to the 4th minus 20x to the 3rd. And then we're going to take the second derivative, which is going to be 60x to the 3rd minus 60x squared. Okay, we're dealing again with the second derivative because it's concavity. So we're going to take that second derivative, set it to 0. I'm going to factor out my GCF, so 60x squared. So I have x minus 1, set it to 0. So I end up with 0 and 1 as my second derivative critical points. And again, we will set up f and f double prime. We don't have any endpoints, so we're just going to keep them open there. We have 0. Oops, we have 1. So we're going to pick a value that's less than 0, and I'm going to plug it into my simplified second derivative. So if I pick, I don't know, negative 1, right, I'm going to get a positive number here and a negative number here. So it's negative, so this is concave down. A number between 0 and 1, so let's say a half. This is going to be positive. This is going to be negative. So again, I have another negative, so this is also concave down. And then a number greater than 1, so 2, I get positive, positive, so that would be positive. Now, just like when we talked about the increasing, decreasing intervals, it's not always necessarily, when you make your chart, going to alternate signs. So usually it does, but you can't assume that it's going to. So that's why we need the chart. So here, it didn't go negative, positive, negative. It stayed negative. So at 0, it's not a point of inflection because we don't have a change in concavity. It stayed concave down through these intervals. So we have a point of inflection only at 1, right? Because that is where it changes from concave down to concave up. So if I wanted to name the point, I would plug 1 into my original function. And when I do that, I get negative 1. I have my interval of concave up is from 1 to infinity. And then from concave down, my interval is going from negative infinity to 1. So it's passing through 0 because 0 is still within that interval. So we're not going to use 0 in there at all. And those are my pieces of information here. So changing topic a little bit, we have the second derivative test. Now this corresponds with what we were doing the previous class with finding the local max and the local min. So it seems a little bit confusing because the first derivative deals with the local min, local max, and the increasing, decreasing. And the second derivative deals with concavity. But you can also use the second derivative to figure out if it has a local min or local max. So it's kind of like almost a shortcut method if you don't want to necessarily have to make the sign chart for increasing, decreasing. You can do the second derivative test and still figure out if there's a local min or local max. So basically what this second derivative test is if you have f prime of c is equal to 0, which means that you have your first derivative critical points, right? If you check the second derivative at the first derivative critical points, if the value is greater than 0, you have a local minimum. And if the value is less than 0, you have a local maximum. All right, so if we look at this graph that's right here, this is the graph of f, right, your original function. So I would have a critical point right here, and right here. Right? That is where my first derivative is equal to 0. Okay, and I can see on here that at this dot here, this creates a cup right here. So that means that this is going to be a minimum. So my second derivative is greater than 0 because it's a cup here. This one is going to be a frown, so that's going to be a maximum. And then here's going to be a minimum because it's another cup. Okay, so we're going to look at an example, and I'll kind of show you both ways so you can see what I mean. So discuss the curve y equals x to the fourth minus 4x cubed with respect to concavity, points of inflection, and local maxima and minima. And then we want to sketch a graph. So I have to find the first derivative and the second derivative anyway because I need to deal with concavity. So I have to find the second derivative. So I have to find the first in order to find the second. So my first derivative is going to be 4x cubed minus 12x squared. And I can, okay, I'm going to factor this just so we have this. So 4x squared I'm going to take out. So I have x minus 3. And the second derivative, y double prime, is going to be 12x squared minus 24x. And if I factor that out, that's going to give me 12x and x minus 2. Okay, so I'm going to show you the two ways to find the local max and min. One way is the way we did it last time, and then the second way is going to be the new way. And I just want to show you how they're related to each other. Okay, so the first way, let me break this up here. So this is the first way that we did last time, and this is using the sign chart. So what we did last time was we took the first derivative and we found the critical points. So 4x squared and x minus 3, set it to 0. So we got 0 and we got 3. Move this out of the way. So then what we do here, right, is we make our charts and we say, okay, we have f and we have f prime and we have our critical points, so 0 and 3. I pick a number that's less than 0. I plug it into here, so that's going to give me negative, which means that my function is decreasing. Pick a number between 0 and 3, plug it into the first derivative. That ends up also being negative, so that's also decreasing. I pick a number that's greater than 3, plug it in. That's going to be positive, so that's increasing. So based off of my sign chart, I can see that it's decreasing, decreasing, and then increasing. So it changes from decreasing to increasing at 3. So I can see I have a local min at x equals 3. Okay, so that is the way that we did it last time. Now the way to also figure this out by using the second derivative test, that, I'll go back really fast so we can see. So the second derivative test is saying, find those critical points, that's what C is, and then plug the critical point into the second derivative and check the sign. So what I'm going to do here is I'm going to do y double prime, which is my second derivative, this function, and I'm going to do that at my critical points. So I have 0 and I have 3. So I'm going to plug in 0. So I'm going to plug in 0 into the second derivative. So this is going to give me 0 times -2, which is 0. Okay, that doesn't help me because in the second derivative test, it says it has to be greater than 0 or less than 0. So when it's equal to 0, it's not going to be anything. So that we ignore. And now we're going to do the second derivative at 3. So I'm going to plug 3 into here. And again, we don't necessarily care about the actual value, but we do care about the sign of it. So if I plug 3 in, that's 36 times 1. So I'm just going to say that it's 36, but I know it's a positive number. So you could just put like plus if you want to. And I know that that is greater than 0. Okay, so since the second derivative is positive, when I plugged in 3, that means I have a local min at x equals 3. Okay, so you could do one or the other. So you could make a sign chart, plug the numbers in, and do this whole thing. Or you can find the second derivative and then plug in the first degree critical numbers into the second derivative and then see the signs. If it's positive, it'll be a local min. If it's negative, it'll be a local max. If it's equal to 0 exactly, it's not going to be anything at that point. Okay, so it's just another way to find the local max and local min. So let's keep going with this problem because it asks us for the local max and min. So it does not have a local max. It does have a local min. And then we want to find the concavity and points of inflection. So I'm just going to continue this on over here. And let me just rewrite this so we have it. So it was x to the 4th minus 4x cubed. And we had found the first derivative, which was 4x squared, x minus 3, just simplified. And we had the second derivative, which was 12x, x minus 2. So now I'm dealing with concavity. So I'm going to look at the second derivative, and I'm going to set it to 0. So 12x, x minus 2, set it to 0. We get 0, and we get 2. So I'm going to make that sign chart f prime with my second derivative critical points. So 0 and 2. I'm going to pick a number that's less than 0. Oops, sorry, second derivative. Pick a number less than 0. So -1, whatever, plug it into your second derivative. So that's going to end up being positive. So that means it's concave up. Pick a number between 0 and 2, plug it in. That's going to be negative, concave down. Pick a number that's greater than 2, so like 3. That's going to be positive, concave up. So let's write this all out. So we have a local min. And that happened, I'm just going to go back here. So that happened when x was 3. So if I want to find the actual point of that minimum, I'm going to plug 3 into my original function. Okay, so I have 3 for the x value. If I plug it in, this is going to give me -27. It's concave up from -infinity to 0 and from 2 to infinity. And then it's concave down from 0 to 2. And then I have a point of inflection. And that happens at x values of 0 and 2. So 0. If I plug 0 into the original function for y, it gets me 0. And if I plug 2 in to the original function, it's going to give me -16. So here I have all the information that they wanted me to find. And then it says sketch the graph of the original function. So I'm going to very poorly probably do a quick sketch of this. So my local min, so 1, 2, 3, let's just pretend for fun that that is, I'll just label it 3, -27, because I'm not counting all the way down 27. Okay. I have a point of inflection, so I'm going to graph my points of inflection and my local mins and maxes. So at 0, 0, and at 2, -16. So we'll call that 2, -16. Okay. So I have these points, but now I have to kind of sketch this graph. And I want to use the intervals of concavity to help me out. So from -infinity to 0, it's concave up. So I have to draw like a cup. Whoops, that's very bad. Hold on. All right, so I'm trying to draw like that. something like that. So if I were to draw tangent lines, they would be below here. So concave up, like a cup. And then from 0 to 2, it's concave down. So I have to connect 0 and 2, but I need it to be angled in such a way that it's frowning at me. So, oops. So something like that. Oops, that's a little bit bad, but it's going concave down. And then from 2 to infinity, it's back to being concave up. So something like, I don't know, this is very terrible, like that. Okay, so we're kind of piecing together the information. So I actually have it graphed on the next slide from the calculator. Okay, so here's our graph. The one I drew, very, very similar. And we can see that here's our inflection points. And then here's our local min, and we can see it's concave up, concave down, concave up. All right, so we're going to look at kind of like a putting it all together slide. Okay, so here we have a graph of the derivative f prime. So down here is my graph. On what intervals is f increasing and decreasing? So right now, we're not really doing any calculus. We're looking at the graph, and we want to see if we can pull out this information. So since this is a graph of the derivative, and we're trying to find out information about the original graph, if the original graph is increasing, that means that the derivative is going to be above the x-axis. So it's going to be increasing, I'll just write increasing from 1 to 6, because that's above. And then it's also above the x-axis from 8 on, so from 8 to infinity. And then it's decreasing, where that means that the derivative graph has to be below the x-axis. So that's happening from negative infinity up to 1. And then it's below again from 6 to 8. Oops, that looks like an infinity. I drew that sideways. My bad. 6 to 8. Okay, so those are our increasing, decreasing. At what values of x does f have a local max or a local min? So remember that local maxes and local mins happen on the derivative graph where it crosses the x-axis. So on the original graph, those are like your hills and your valleys, those bumps. But on the derivative graph, it is where it crosses the x-axis, because that is where the derivative is equal to 0. So I'm looking to see where it crosses the x-axis. So it crosses here, here, and here. So at 1, it's going from below the x-axis to above the x-axis. So it's going from decreasing to increasing. So that means that's going to be a local min. So I have a local min at wherever it's going to be going from above to below. So that happens at 1, x equals 1, and at 8, because it's going from below to above. That means at 6, because we're going from above the x-axis to below the x-axis, that is a local maximum. So local max happens at x equals 6. Okay, so I'm going to get rid of that. On what intervals is f concave up or concave down? So now we're dealing with the concavity. That's dealing with the second derivative. Since we have the graph of the first derivative, that means that we're looking at the derivative of this. So if the original graph is concave up, okay, on the actual graph, it would look like a cup. But on the first derivative graph, we're looking to see where the slope, because the slope is the derivative, where the slope is positive. So the slope is positive here, here, and here. Oops. So it's going to be, I'll put CU for concave up, from negative infinity to 2, and then from 3 to 5, and then from 7 to infinity. And then it's concave down, where the slope is negative. So let me get rid of this. So the slope is going to be negative, oops, there and there. So it's going to be from 2 to 3, and then again from 5 to 7. And then it says to state the x-coordinates of the points of inflection. So the points of inflection, that's where it changes from concave up to concave down. So when we're looking at the first derivative graph, we're looking to see where the slope is changing. So I can see that the slope is changing from positive to negative here, negative to positive here, here, and here. So really, on my first derivative graph, it looks like the local mins and maxes. So my points of inflection are going to be at POI is going to be at x equals 2, at x equals 3, 5, and 7.